Hello, this is Team 17, and I'm Rory.
I'm Sterling.
I'm Marcello.
I'm Ihan.
And this is Great Big LED Circles.
The rover developed in this project has been designed and programmed to highlight LEDs in a playing field by encircling them with Sharpie. A user can place any number of LED indicators on a large play area, and the rover will locate each indicator, navigate towards it, and draw a circle of a matching color around it. Once it has drawn a complete circle, it will look for the next nearest indicator until each LED has been highlighted.
Here you can see the rover beginning its search procedure. It starts with a full 360-degree spin and notes the location of the nearest object it detects with the IR sensor. Then it performs another rotation and stops when it faces the object that it has detected. Next, it begins proceeding towards the detected object, and if it loses tracking of the object, it begins its course correction by rotating left 55 degrees to perform a 90-degree arc in attempt to relocate the object. When the rover detects that it is close enough to the object, it closes in on it by going in a straight line, knocking over the object, and positioning the rover so that it is centered over the LED. Next, it uses the color sensor to detect which color LED it is centered over and proceeds to use the robotic arm to grab the marker of the corresponding color. The marker is then placed in the active marker holder, whereupon the device begins a full spin to draw a circle around the LED. The arm then replaces the active marker, and the rover begins another searching spin to locate any additional markers, prioritizing the nearest one that is detected.
This is our rover. It is composed of a dual motor assembly, a chassis, a robotic arm, a motor controller, a Wi-Fi and Wi-Fi shield, an IR sensor, and a color sensor.
The infrared proximity sensor, or IR sensor, gives readings that can be converted to distances using the ADC pins of the PIC. In the project, the IR sensor is used to detect which object is closest to the rover so that it can assist with pathfinding of the nearest object. The TCS3200 color sensor is used to detect the color of the LED the rover is centered over. The way the sensor works is that it consists of an 8x8 array of photodiodes. 16 photodiodes have blue filters, 16 have red filters, and 16 have green filters. These photodiodes are connected to a current-to-frequency converter, which produces an output square wave whose frequency is proportional to the intensity of the chosen filter. Only one color filter can be selected at a time, and this color channel is picked by using two pins, S2 and S3. To measure the frequency, we have to record the time for how long the square wave is on or off. To do this accurately, the PIC has to be in a known state. To do this, we wait for the falling edge of the signal, then we wait for the rising edge, then we wait for the falling edge again. Once the signal is low, the timer starts and begins counting. When the signal goes high, we stop and store the value of the timer, which is inversely proportional to the frequency. We store 3 readings, one for each set of red, green, and blue photodiodes, once their corresponding pins are enabled. The values are then run through the color API to determine which color is detected, either red, blue, or green. The information is then relayed to the PIC, and the arm takes it from there.
The rover communicates with a server that is used to store and retrieve important data, such as duty cycle constants, and also to display information about the current state of the rover. The data is sent using the HTTP standard, with message contents stored in JSON format. Both the server and the PIC check for message integrity and framing to ensure accurate communication and to discard corrupt or incomplete messages. Communication between the server and the PIC is done using a Wi-Fi. The Wi-Fi communicates with the PIC using UART so it is able to receive and transmit simultaneously. Threads that need to send or receive information using the server do so using a server message API. A thread running on the PIC sends requests from individual threads to the server and adds framing and other required formatting for HTTP messages. Another thread running on the PIC routes responses from the server to the threads that requested the information, and transfers this information to these threads via their respective message queues.
We used only 2 types of message queue because we used the tag union. The first type of message queue is used for inter-process communication. It is a tag union that consists of several data types. The second type of message queue have only one string, and it is used to send the HTTP requests to the URTX thread. A set of APIs, which is a wrapper for the FreeRTOS message queue function, is written for convenience. The APIs include create message queue, send message queue blocking or non-blocking, receive message blocking or non-blocking.
The rover uses a state machine running in a control thread to operate and control interactions between the components, and run a pathfinding sequence to find the LED markers. The state machine operates by starting in search mode, where the rover completes a 360-degree turn while measuring the distance with the IR sensor every 5 degrees. The rover then turns again to face the direction of the nearest object it detected. After this, the rover begins driving towards the object while continuously measuring the distance between the object and itself. If this distance ever grows, indicating the rover is off course and measuring something behind the intended object, it will go into a course-correct mode. In this mode, the rover rotates 55 degrees left and scans a 110-degree arc trying to reacquire the object. If the object is not found again, the rover returns to its initial search mode. If the object is found, however, the rover returns to driving forward. Once the rover detects it is close enough to the object, it closes the distance and centers itself above the LED.
The robotic arm used by this project has 4 degrees of freedom. It can rotate in the x-axis, move forwards and backwards in the z-axis, lift up and down in the y-axis, and open and close its jaws to grip objects. Each of these movements is controlled by an independent 5-volt 2-gram servo, whose position is controlled by a custom sequencing API. Said API takes ordered commands from the system server and schedules them for the servos to execute in a specific order, which results in the final sequencing and movement that you see in this video. All 5 servos receive their position information from the API in the form of a varying duty cycle on a single control line. A duty cycle is best described as the percentage of time a signal is held high within a specified period of time. Different duty cycles correspond to different positions for each of the independent servos. From a hardware standpoint, each duty cycle is controlled by a peripheral called an output compare, which varies the state of the control line being read in as a duty cycle. Ordinarily, each servo would require its own individual output compare to operate. However, in order to fully integrate each component of our final project, only one output compare was used to control all 4 servos. Using a timer with a period equal to 1/4 of the period of the output compare, the output of a single OC was multiplexed to all 4 control lines of the robotic arm. This allowed for other systems, such as the motors, to use resources on our controlling board.
The rover uses 2 motor assemblies. 2 motors in the left side connects to 1 motor controller, and so does the other side. The motor's feedback, which is a clock signal, is connected to the external clock source of timer 3 on the PIC32 board. The motor's speed is controlled by the PWM signal's duty cycle. The higher the duty cycle, the faster the motor spins. The proportional controller is used to control the motor. The motor can relatively precisely move a desired distance or turn a desired angle. This is done by using the timer's interrupt from timer 3. For example, if the motor had to move 10 centimeters, the period of timer 3 is set to a value that converted by the gain of the proportional controller. The interrupt will be triggered once the motor has moved enough distance. The interrupt will then send a message to the motor thread that's blocking while the motor is moving. After the message is received by the motor thread, it will then stop the 2 motors by setting the duty cycle to 0. The constraints that were met are the following. The entire rover is light enough to drive under a single battery bank. The robotic arm is precise enough to pick up the markers and put them back. The motors are precise enough for the navigation to work smoothly. The server can handle dropped packets. The one constraint that we haven't met is that the server handles poorly when the network traffic is high.
We have a fairly reliable project. Our arm and motors pull the server regularly to ensure that any dropped packets do not lead to undefined behavior. Our Wi-Fi is set up to auto-reconnect just in case it is disconnected from the server. Additionally, the messages sent and received by the Wi-Fi are framed to ensure completeness. Our pathfinding sequence can correct for sensor errors and allows the system to run unaided until it is finished. The system only pulls the color sensor once the rover is positioned optimally over the LED. The arm moves in small increments as to not overburden the servos by moving too quickly. Conversely, there are some reliability errors in that our servos in the arm are weak and may wear out over time. Human error on marker placement on the playing field may lead to inaccurate color detection. The motor controller is not accurate enough for fine adjustment of pathfinding during our navigation algorithm.
Our project is also robust. It has a sturdy build in large part due to the wide wheelbase and strong mounting hardware. The flared marker holders account for percent error when the marker is dropped, so it has a higher chance of being placed back to its original position. The internal tracks of the rover are optimized to not bind up. A rim of glue is around the markers to allow for tolerance in arm grip and vibrations. Server setup account for dropped or incomplete messages and continue communication even after any unexpected disconnections. The rover can operate on any playing field area up to 80 centimeters radius. However, the floor must be white, but there can be a variable number of markers.
Some ideas we would have liked to have implemented if we had more time for this project include a more strong arm to better grab the pens, some more fine motor control via the implementation of more precise motor drivers, and more precise motors themselves. We would have also liked to have had a color sensor with a broader area of detection to allow slightly less precise positioning of the rover.